Welcome to the video on phase diagrams. This is section 11.6 in your book. I would highly recommend that you take a look at 11.6 along with this video just to make sure that you get the information in multiple ways because this is probably new for most of you. So a phase diagram is just a graph of pressure versus temperature for a substance. So what it shows is it shows the state of a substance at various temperatures and pressures, and it shows the places where equilibrium exists between phases. So what you can see on a phase diagram is you can see the melting, the boiling, and the sublimation points at different pressures. So if you take a look at this phase diagram, you can actually see that the green region is solid, the blue is liquid, and the yellow or the orangish color is a gas. So anything on this line actually represents melting if you're going solid to liquid, or freezing if you're going liquid to solid. It also shows the triple point and the critical point, which we'll talk about in a second. And like I said, it shows where equilibrium exists between the phases. The phase diagram, it's just a great way to summarize all of the conditions about a substance. So you can actually see solid, liquid, gas, where it melts at different pressures or different temperatures. And so all of this is actually going to be based on reading a phase diagram. So can you read a phase diagram? Can you tell at a specific pressure what temperature we're at, things like that. So, like I said, phase diagrams tell us which phase will exist at a given temperature and pressure. Specific features of a phase diagram. The first thing is we can see the vapor pressure curve. And this blue curve right here is actually the vapor pressure curve. So this is the curve that exists when liquid and gas is at equilibrium. What this just means is anything on this blue line is a liquid and a gas at the same time. The vapor pressure curve actually ends at the critical point, and at any temperature or pressure above this critical point, the liquid and the gas phases are indistinguishable. You can't tell the difference between the liquid and the gas phase, and this substance is then called a supercritical fluid. And a supercritical fluid is a substance that takes on properties of both liquids and gases. So a supercritical fluid actually fills its container like a gas, but the molecules are still closely spaced together like a liquid. And so this critical point, it's just the critical temperature and the critical pressure for a gas. So this is a pairing of temperature, which is on the x-axis, and pressure, which is on the y. We can also find the normal melting point. So the melting curve is actually this green curve right here. And this green curve just separates the solid from the liquid phase. Each point that is on the curve is an equilibrium between solid and liquid. So you would have both states of matter at that point. Typically the melting curve slopes slightly to the right, like you see. And this is because substances that are in the solid phase are more dense than the liquid phase. And as you increase pressure, you're actually increasing the closeness of the molecules. And so usually when you increase pressure, it more favors the solid phase because they're already more compact. And so therefore higher temperatures are required to melt the solid as you increase the pressure. And so then that melting point, if it's a normal melting point, that means that it is the melting point at 1 atmosphere. Then we have the normal boiling point. And so the boiling point, like was mentioned in the last video, is simply when a liquid boils at 1 atm. So it's going to be the temperature at which a liquid boils when you're at standard pressure. And then we have the triple point. So the triple point, which is right here on the graph, is the temperature and the pressure at which all three phases are in equilibrium. So what that means is at this temperature and pressure, you have solid, liquid, and gas all at the same time in a container. So any temperature and pressure combination, so any XY coordinate that is on a curve, so whether it's on the melting, whether it's on the vapor pressure curve, or even the sublimation curve, which is this red curve, if you have a combination and the point is on the curve, that represents two phases because they're in equilibrium. They're either melting or boiling or freezing at the same rate, and so you actually have both states of matter. Any temperature and pressure combination that's not on the curve, so if we have a point that's out here on the graph, that just represents a single phase or a single state of matter. So the critical temperature, I mentioned the critical point, and the critical point gives us the critical temperature and the critical pressure. So critical temperature is the highest temperature at which a substance can exist as a liquid. Above the critical temperature, a gas can no longer be liquefied, so condensation can no longer occur. And anything above the critical temperature, the kinetic energies of the molecules are greater than the attractive forces, so they're greater than the intermolecular forces, and therefore it can no longer exist as a liquid. The greater the intermolecular forces, so the greater the attractions between the molecules, the higher the temperature has to be to overcome those intermolecular forces, and so the higher the critical temperature. The critical pressure is just the pressure that is required at this critical temperature. So it's kind of the pairing at the critical temperature. So just this generic phase diagram. We always have three states of matter. The solid is usually all the way to the left. Then we have the liquid, which is usually kind of up in the corner. And then we have the gas or the vapor phase, which is underneath the solid and the liquid curve. So remember that the liquid vapor equilibrium, so the gas pressure curve, it starts at the triple point, which is where all three states of matter are in equilibrium, and it ends at the critical point out here, which is when liquid and vapor are indistinguishable from each other. So we have the sublimation curve. So the sublimation curve is the equilibrium between solid and gas. If we go solid to gas, that's sublimation. If we go gas to solid, remember that is deposition. And then we have the melting curve. And so the equilibrium between the liquid and the solid, this is the melting point at each pressure. So this actually allows us to see the melting point as pressure increases. And then we have the vapor pressure curve. So as we go liquid to gas, that is vaporization. As we go gas to liquid, that is condensation. So we have the critical point out here. Remember, anything above the critical point, liquid can no longer exist. And this is the supercritical fluid. And the triple point is where all three exist as equilibrium. Now, what I want you to notice are the three states of matter and where they are the most stable. So notice that the gas phase is stable at low pressures. Notice the pressure is low down here and at high temperature. So gas is stable at low pressure and high temperature, and the solid is stable at low temperature. Right? Notice the x-axis is temperature, so low temperature and high pressure. And then the liquid phase, well, that's just stable that in the region between the solid and the gas phase. So poor liquid, it always gets kind of thrown right in the middle of the solid and the gas. So with water, the phase diagram of water is unique. Notice first the high critical temperature and critical pressure. So the critical point right here. Notice how high it is. This is because water has very strong intermolecular forces, right? So it has dispersion, which exists in everything. It has dipole-dipole because it's polar, but it also will hydrogen bond to attract water molecules because we have H and O. So notice how high this critical point is. Another unusual feature is the slope of the solid-liquid line. So remember I said most phase diagrams, it's going to slope slightly to the right. Well, the slope of this solid-liquid line actually slopes more to the left and it's more negative. Well, this means that as the pressure is increased, the water goes from solid to liquid. And this is because the solid phase is actually less dense than the liquid phase. And so that's why this phase diagram is actually slightly unique. Remember I said water is almost always an exception to everything, and with phase diagrams, that is still the case. So with phase diagrams, there is this website, chemguide.co.uk. I'll post this on the class website, but this just has more explanations of phase diagrams. So if you want to take a look at some different phase diagrams just for some extra practice, I would recommend going to this website just to get some extra practice. So that is it for this video. Make sure that if you have questions that you ask me. Again, read section 11.6, especially after you watch this video. Hopefully it will make more sense the second time that you're going through the information.